Okay, we're going to combine sections 13.3 and 13.4 into one section. They're really short. They correlate to each other somewhat, but save time. 13.3 should talk about arc length in space, and 13.4 should be talking about curvature, and I'll go over that really quickly with you. Length of a curve. This is section 11.2 in our book, right? Depending on which book you use. If you use Stewart, that's chapter 10.2. Says if you have a curve that's defined parametrically, in which x is a function of time and y is a function of time, and t is between the interval is on the interval between a and b, then L equal the square root of ds, if you remember back in the days from 11.2, where s is the actual curve. If you remember this, again, this is in the previous course, this is described fully. And it was L equal the integral of ds. Oh, right there. That's what L equals. So this is in 2 dimension. It's the square root of f prime of t squared plus g prime of t squared. Now, if I take a derivative of this vector, I know that's f prime of t, g prime of t. And the magnitude of the derivative is really what they have to be the length of the interval, the length of the curve. So the length of the curve is really nothing more than the integral from a to b of absolute value of r prime of t. I'm going to even add a piece that's not in here. If I want to be really picky, if r is describing the curve, r prime is the velocity. Now for 3D, it carries on the same deal. Given f, g, and h, interval between a and b, well, L is the integral of ds from 11.2. That is, if you take a derivative of this, f prime, g prime, h prime, and the magnitude of that, that turns out to be the length of the interval. So, given the following curve, and we know what that looked like, no need to graph it, but you could if you want. Find a unit tangent and find the length of the curve. Unit tangent, that's preparing you for curvature. Unit tangent, well, let's see. A tangent vector would be right? And to make it a unit tangent, so I'm going to refer to that by t. A unit tangent vector is really r prime of t divided by the magnitude of r prime of t. Isn't that how we make a vector unit? So what is the magnitude of r prime of t? In this case, it turns out to be the square root of sine squared of t. I should write it in for your notes. Negative sine of t squared plus cosine of t squared plus 1. Isn't that a 1? So, the unit tangent, which is I, would be negative sine of t over radical 2, cosine of t over radical 2, and 1 over radical 2. That would be my unit normal. As for the length, and again, if you really think about the unit normal, it's really the velocity. That's really v of t divided by the magnitude of v of t. I'm using v lightly. I didn't put an arrow on it. F, forgive me. And what if I wanted to find the length of the interval? Well, the length of the interval, L equal the integral, and I suggest you start getting used to these notations. L equal the integral from 0 to pi over 2. ds is nothing more than the square root of, so the magnitude of this. We already found that. No need to do it again. I could say that is negative sine of t and redo the work one more time, right? Or I could simply say, hey, look at the first part. That's radical 2 dt. So that's radical 2 times t evaluated from 0 to pi over 2. Radical 2 times pi over 2 minus 0. Okay, I'll get it right. And that would be radical 2 pi over 2. If I look at part B, the same deal. Well, this is pretty much like a section. There's a piece that I'm going to use in my curvature, which is the next section, and combine them into one. So if I really wanted to find a unit tangent, T for tangent, that's going to be R prime would be a tangent, but to make it unit, I'll divide it by the magnitude of T. So I need a derivative, and I need the magnitude of that. Well, let's see. What's R prime? Again, keep in mind what R prime is. I want to point this out as we move on all throughout this course. That is 1, 2t, and 2t squared. Is that right? Yeah. And the magnitude of R prime of t is square root of 1 plus 1 squared plus 2t squared plus 4t squared. Oops, I'm doing things in my head I shouldn't. 1 squared plus 2t squared plus 2t squared squared. More space. I have plenty of space. Magnitude of R prime of t is going to equal the square root of 1 plus 4t squared plus 4t to the 4th. That's factors, luckily. So the magnitude of R prime of t is nothing more than 1 plus 2t squared. So this is not given for me for part I, not to find the actual tangent. This is given for the length. So I would say this is 1 over 1 plus 2t squared, 2t over 1 plus 2t squared, and 2t squared over 1 plus 2t squared. You can clean that up a bit, play with it, but that's all I need. That would be my unit tangent. By doing this, automatically I have already figured out the length of the vector. So in the second part, when I say what's L, that's the integral of ds, well, that is really the integral from 0 to 3 of what? Well, isn't ds right there? So that's why it makes sense to really do this section one shot. Both sections, because there's a lot of repetition. 27 on a test you've done right there for the homework. You're going to say that is 3 plus 18, 21. If I make a mistake on the calculation, just make sure you follow the procedure of how to solve this. So that's one section. Actually, the unit tangent is not in section 13.3. It's only in 13.4, but I wanted to use it to show you how they're going to overlap, and that's why I'm covering both of those together. Now let me show you what a curvature is. Curvature, given a smooth curve defined by r of t on an interval I, on some interval, r prime is continuous and r prime does not equal to 0 on that interval, then here's my unit tangent. We just did that in the previous. I didn't need a definition for that. To find the tangent vector, I take a derivative. To make it a unit vector, I divide by its length. But now it's official. That indicates the direction of the curve. So, if this curve happened to have the following direction, if you pick a point P, let's say you pick this point. At a point P, the tangent, unit tangent, will be pointing in the direction of the actual direction. So, T and the direction of the curve will match. And N of T is a unit normal. What is that? That is the derivative of T divided by its length. Now let's see if that makes sense. I'll talk about that in a minute. So this unit normal, really, if you think of a circle, I'm going to use a color that's a bit hard to see. If you think of a circle touching at that one point, so the tangent will be flying off straight and the normal will be actually pointing toward the center. Now let's put everything in perspective. We did this already in the previous section. I know you didn't pay attention, which is why I'm bringing this up right now. So given r of t, isn't the velocity r prime of t? Didn't we graph that in the previous section? And isn't the acceleration the derivative of t of the velocity, which is r double prime of t? Wouldn't you agree, if t is r prime, then the derivative of that will be r double prime? And didn't we show in the previous section that given any shape, if you take a point at a given point, the velocity will always be pointing in the same direction and the acceleration will always be pointing toward the center? That's the curvature. If this is the curvature, that circle, if that's this curvature at that one point, then that's how the tangent and the normal will point. They're perpendicular to each other. Now to find the curvature, there are many formulas. The best one I like, this is my personal preference. There are more than what I'm showing you. Or you could even go by this. That's how you find the curvature at any given time. So it's up to you what to do. Now if they ask for the tangent, then probably, since you have to find the tangent, since you need to find r prime and the magnitude, well, guess what? This is already right there. All what you have to do is take a derivative of this and find the magnitude of it. You want to stick with the cross product divided by the magnitude cubed. That works as well. It's the same answer. So now they're asking for two more things. Again, given r of t, find a unit tangent. Well, let's see. I know to find the tangent. This is the tangent to the curve, right? The magnitude of that is actually the square root of 2 squared plus 30/60 squared. I could clean that up a bit. I could factor a 4 out. Now, the unit tangent in this case that would be 2 over 2 the square root of 1 plus 90 squared, and 60 over twice the square root of 1 plus 90 squared. So my actual tangent is 1 over square root of 1 plus 9t squared, 3t over the square root of 1 plus 9t squared. There, I got one of them. To find the normal, the unit normal, so keep things in perspective. I did put an arrow on that thing. Yeah. The unit normal is the derivative of this divided by the magnitude of r prime of t. Again, the formula is right there. The magnitude of r prime of t I already found. That I already know. That is the square root of 1 plus 9t squared. This, oh, with a 2. Look at that. Almost forgot because I was looking at this. My mistake. Now, what is the derivative of this? Well, that's a lot of work. It's kind of a mess, right? So I could say that's 1 over multiplied by, and let's see how that works. What is t prime? T prime is, and let me get just a bit more space. It's not liking it. T prime would be, well, let's see. That's going to be 1 plus 9t squared to the negative 1/2. So bring the power down, subtract 1 from the power. Times 1 plus 9t squared to the 3/2 times the derivative of the inside, which is 18t. And here I need the product rule. I mean the quotient rule. Derivative of the top times the bottom. So again, not a lot of fun. Minus the top times derivative of the denominator. All over the denominator squared. Now I know this is a big mess. I keep on missing the arrow, which is a big deal. That is 9t over 1 plus 9t squared to the 3/2. And here, if I get a common denominator, that is 6 into 1 plus 9t squared minus, oh, I could have saved myself some work. 2 divides 9 times. So it's 3 into 1 plus 9t squared minus 27t all over 1 plus 9t squared to the 3/2. And if I put that right here, pretty much I'm done. Again, I normally do not worry much about normal. I bring it up on the homework. I rarely bring it up on the exam. That is 27t squared minus 27t plus 3 all over 1 plus 9t squared to the 3/2. So that is my normal vector. So on the homework, I suggest you attempt to find the normal on one of the problems and ignore the other one. Now, curvature, you have multiple options. These are 4. I have a lot more formulas than this. If you want to find curvature, you could do this. You could use this. The fact that I already figured out everything here. Well, the magnitude of t prime. T prime is right there. The magnitude of this, do you see how messy that is? But I could write it out if that's the case. If I'm not going to work it out, I could say that is the magnitude of this. So that is the square root of, whoa, I spoiled the surprise. That is, I could say the square root of 9t divided by 1 plus 9t squared to the 3/2 plus the j component, that monster. But actually, I'm sorry. You know what? (27t² minus 27t plus 3 divided by 1 plus 9t² to the 3/2, right? It's right there actually. Divided, again, a massive mess. But the application is extremely useful, over the magnitude of r prime cubed. And there it is, done. Now, of course, I could take r, take a derivative, take two derivatives, cross them together, divided by the magnitude of r prime cubed. I'll probably do that on the next problem. But since I have to find t and n, might as well use it. Not that it makes it really simple or really easy. Curvature is always a big mess. Whenever I test you on it, I have to pick my problem wisely. Otherwise, you could spend a really long time on that. Alright. It seems I made a mistake. I apologize. I didn't pay attention that the normal is divided by, oh boy, magnitude of t prime of t. That's really what I meant to say. So the denominator should be, it shouldn't be this. The denominator should be the square root of, oh boy, square that component and square that component. Sorry about that, my mistake. The rest should all be fine. So the same deal here. I am going to find the tangent, and I'm going to go straight for the, I'm not going to find the normal on this problem. So if I want to find the tangent, well, I know what a tangent is. A derivative. Isn't that negative 3 the sine of t, 3 the cosine of t, and a 2? And so this is tangent to the curve. I know that already. But I need it to be a unit, so I need its magnitude. Square root of 9 sine squared of t plus 9 cosine squared of t plus 4. Factor a 9 out. Sine squared of t plus cosine squared of t. Isn't that a 1? Doesn't that mean that this is the square root of 14? So let me go on the side and say, look, r prime is negative 3 the sine of t, 3 cosine of t, and a 2. The magnitude of r prime is 14. So out of those two, this is what I know. T is negative 3 the sine of t over 14, 3 the cosine of t over 14, and 1 over 7. There's the first thing they wanted me to find, and I found it. Okay, got it. Now what? Now I want to find, you know what, might as well, let me find the unit normal. N of t would be what? N of t would be, well, the derivative of this divided by 14. So that's going to be, what's the derivative of this? Isn't that negative 3 over 14 the cosine of t? negative 3 over 14 the sine of t, and a 0. That's not n of t, that's really t prime. N of t is t prime divided by the magnitude of r prime of t. Right? And it's right. Oh, sorry, magnitude of t prime of t. Did I do that? Yeah, I did. So I need to take a derivative of t. I got it. N of t is t prime divided by the magnitude of t prime. So that is negative 3 over 14 cosine of t, negative 3 over 14 sine of t, and a 0. And what I need to find the magnitude of t prime. The magnitude of t prime, the magnitude of this is the square root of, isn't that 9 over 14 cosine over 14 squared cosine squared of t plus 9 over 14 squared sine squared of t? Isn't that the square root of 9/14? I know. Yeah, you factor that out of those, that's what you get. So, if I'm going to divide by this, wouldn't that be the square root of 14 over the square root of 9? And of course that simplifies. That's radical 14 over 3. And that would be negative radical 14, the cosine of t over 14, negative radical 14 over 14, the sine of t, and a 0. So again, a lot of work. I normally don't bring a normal on a test unless it's something very basic. Not because it's hard, just because it's long and a bit tedious. Just a bit. Now, if I want to go and find the curvature, again, I could use either of these. I already have almost everything that I want, right? So I could say, you know what, let me go ahead and use it, or let me go ahead and figure out r prime crossed with r double prime divided by the magnitude of r prime cubed, right? I'm just looking if I copied it right. Yes, I did. So that's going to be the cross product. Again, I have plenty of space. Let me do that. So if I take r prime, that would be what? R prime would be negative 3 the sine of t, 3 the cosine of t, and a 2. If I take r double prime, the derivative of that will be 3 the cosine of t negative, negative 3 the sine of t, and a 0. And if I cross those, what do I get? The I component, I'll get negative 6 sine of t positive. J component, I'll get 6 cosine of t. And the k component, I will get 9 sine squared of t minus, plus 9 cosine squared of t. Okay. So, wouldn't you say that this is 6 sine of t, negative 6 the cosine of t, and that's just a 9? So the curvature is the magnitude of this. If I take the magnitude of this, that would be the square root of 36 sine squared of t plus 36 the cosine squared of t plus 81 over the magnitude of r prime. There is r prime. The magnitude of that, that's the square root of 9 the sine squared of t plus 9 the cosine squared of t plus 4 cube. Almost there. And curvature would be, if you factor a 36 out of both of those, you'll have 36 into 1. 36 plus 81, what is that? 7, 117, and this, if you factor a 9 out, that's 9 into sine squared plus cosine squared, which that's 14. And I don't know if that divides evenly. 7, 9, 2, well, whatever that is. Now something I want to show you. This is a bonus. Given y equal f of x, a function. If I take y equal f of x, and I write that as a vector, wouldn't r prime of x equal 1 f prime of x? And wouldn't r double prime equal 0 f double prime of x? If I take r crossed with r prime, isn't that I could add the 0, but that's going to be, so you could make it 3 if you really want. You could add the 0, 0 and go from there if you really like. It's not going to make much of a difference. You're going to end up with f double prime zero, 0. So if I say what's the magnitude of that, wouldn't that be the magnitude of f double prime of x really? And if you would have left it at 2 by 2, which, you know, no big deal, for a 2 by 2, wouldn't you say that is f double prime of x minus 0? So when I say the curvature is r prime crossed with r double prime magnitude, well, isn't that really this? Over the magnitude of this, isn't the magnitude of this 1 squared plus f prime of x squared squared cubed? So if they gave me a function, I could simply just use those formulas and proceed. There's not much to do. And of course, I could go from 2 if I want. I could write that as a vector, even in terms of t, and say if x is t, that's t cubed, and proceed and do all of that work. Or I could say, forget it. Why should I do that? The curvature is really the magnitude of f double prime. What is f double prime? So f prime is 3x squared. F double prime is 6x. So the curvature is absolute value of 6x over 1 plus f prime squared. That is 9x to the 4th, all raised to the 3/2. And there it is. If they give me a value for x, I could evaluate that. That easy. I could take the cross product and do what I did, but you know that's a lot more work. What if I did another problem, since I have another 10 seconds to do another problem, or 30 seconds? Well, what do I need? I need two derivatives. What's f prime? That's the cosine of x. What's f double prime? Negative the sine of x. The curvature would be, according to my formula, f double prime over the square root of 1 plus the cosine squared of x cubed. If you give me a value, a point, I could tell you exactly what the curvature is. And that's pretty much two sections in one. Again, the only reason we're covering two sections, we're going to spend more time on later on sections that require a lot more and more complex theory than this.